Hello everyone, and welcome to today's webinar. Thank you very much for joining us. On behalf of Tornado Spectral Systems, I would like to thank you all for attending. My name is Omar Abbasi, Marketing Associate at Tornado, and I'll be your moderator for today. Today's keynote speaker is Dylan Jones, Principal Scientist at Sanofi UK. Following his presentation, we'll move into a live Q&A session where you can pose questions to today's webinar. And you can submit questions directly to me using the chat box located within the menu. About our speaker, Dylan has over 20 years of experience within the pharmaceutical industry and currently heads the analytical chemistry department at Sanofi UK in Haverhill. Within his group is the Center of Excellence in Process Analytics, which provide PAT services. Dylan's group actively pursues innovation in advanced manufacturing and control. So without hesitation, may I pass you on to today's speaker, Dylan Jones.
I'd like to thank Omar for this opportunity to, I suppose, talk a little bit about things that are very close to my heart. So I shall kick off then with two quotes that are my favorites for this year, and they're pretty much different ways of saying the same thing. It ain't what you don't know that gets you into trouble, it's what you know for sure that just ain't so. The other, in theory, there is no difference between theory and practice, but in practice there is. Now these two messages, I guess, are quite important to me when trying to sell the idea that people who are already very experienced in the industry and already know their stuff ought to perhaps go back and assess some of their assumptions. And I guess, so a lot of the things that I'll be talking about today hopefully will challenge some assumptions that you have about the way you do your business. Okay, next slide, please. So there are three things that I hope you will come away from in this webinar today. The first is you'll understand when process analytics are needed in advanced manufacturing, understand some of the challenges in implementing the analytics successfully, but also understand some of the particular benefits that, that Raman spectroscopy offers us. Next slide. So these are the topics that we'll be covering at an introduction. I'll be talking about better processes. I'll be talking about inherently controllable processes and what that means. It's always worth talking about some of the challenges around multidimensional PLS calibrations. And then I'll give you a specific example of a multivariate calibration that we built for a very complex process with many variables. Of course, not all your problems can be solved with your equipment or with your PLS calibration, but there's also other places where issues of precision and accuracy can be addressed, and these can be done using noise filters. And then finally, I'll talk about some of the caveats around industrial installations. For those of you who've spent most of your time in sort of R&D environment, working with production has some particular challenges. So why do we need better processes? Well, to me, a better process means better control of that process, better product, narrower manufacturing tolerances, that sort of thing. I guess, why do we want those things? Well, we're looking for better patient outcomes. We want a more consistent dose to the patient. We want fewer side effects. You know, the things that we add into our tablets that, or our injectables that we put in our patients that we really don't want to be there. We'd like to reduce the cost of manufacturing. We're constantly under price pressure, so that's something to manage. Regulatory expectations are changing as analytical techniques improve. So as we are able to interrogate specifically bioprocesses in more detail, so the expectations increase as well. And as mass spec is allowing us to sort of study proteins, their primary, secondary, tertiary structures, and to see how those affect efficacy, this is becoming a bigger and bigger topic. The business is changing. Increased flexibility may be required. So what this means is that going forward, a lot of the products that we manufacture will be for increasingly small niches. As stratified and then eventually personalized medicine makes its way into our business, the patient populations are going to be getting increasingly smaller, and so we need to be flexible and light on our feet when addressing those needs. The process defines the product. For anyone who's worked in biotech, the way in which you develop or operate a process has a huge impact on the physical and sorry if I'll get this right, on the behavior of say for example a protein, the level of glycation, the protein folding. These are all affect efficacy, and to be able to control these as a manufacturer gives you a unique product that other people will find it very difficult to copy, because you can't just simply grow some cells and hope to make the same product. It's a bit more complicated than that. Finally, the other point that I wanted to make was that yields in upstream processing have increased enormously in the last few years. People are making better cell lines that are much more productive. And so the bottlenecks are now in downstream processing. And you could conceivably arrive in a situation where you can make protein faster than you can purify it. And you could end up throwing stuff away. So obviously being able to process stuff faster would be a huge benefit. Next slide, please. So better processes then, and the requirements of better processes. There are 3 items here. You need a process to be inherently controllable, which I'll talk about shortly. And we need better design control philosophies. The way we run processes at the moment are, in many respects, too simplistic. Things like PID control work up to a point, but there's so much more potential. Running a batch the same way at the start of the batch, again for bioprocessing, at the start of a batch and at the end of the batch makes no sense to me. The cells need different things at different stages in the process. So if you want to optimize growth and protein expression, then you need to have a sensible control philosophy that manages those different areas. And here we're talking about model control systems. And then finally, we need capable and reliable measurements to make it all work. You can't control a process if you can't understand what's going on at any moment in time. So before I move on, there's just to waffle a little bit about capability. This is a statistical term. It doesn't just mean literally a capable process. Capability is a statistical term referring to the variation in the process. So I've drawn a very simple graph below. The red line shows a 3 sigma process. This is a process that is statistically capable. It is, or neutral even. Anything less than 3 shows your process is statistically out of control, and anything better than 3, your process is in control. The pharmaceutical industry, believe it or not, battles to achieve 3 sigma processes. There are a significant proportion of products produced by pharma that do not meet the state of statistical control. And it's, I won't go into the pros and cons of that, but I just wanted to show you in the next graph, a 6 sigma process is the one within the blue line, shows that simply by halving the noise or the uncertainty in your measurement, you can reduce your fallout rate or the number of failures from 0.3% down to about 2 parts per, or 2 items per billion. So simply by halving the uncertainty in a process, well, in a 3 sigma process, you can significantly reduce the probability of making faulty product. So what my group is heavily involved in is trying to create processes that are 6 sigma. Next slide, please. So here's a typical installation, just to give you sort of a sense of the sorts of things that we're talking about. We have a biotech process. It has a spectrometer. We acquire information through the probe. We then take that spectrum and we put it through a calibration, normally PLS, through the PC. Next one. We then take that signal and we clean it up using noise filters. So we extract the measurement from all the other bits of noise that are going on in our system. And then finally, we use advanced process control, which I alluded to earlier. That I'm not going to talk about much today. It's a topic in its own right. So if we move on then to inherently controllable processes. Next slide. It's moving, thank you. Now I've got some very simplistic drawings here, and I'm going to have to explain to you exactly what my simple drawings are. So on the left-hand side, you have a column showing a stable process, and that is supposed to be a drawing of a marble in a cup on a table. And as long as your cup is in the right place on that table, I'll put a little mark there to show that where the right spot is, my marble will always sit in the place that I want it to be. So this is a stable process. As long as everything is set up right, the marble sits exactly where you want it to be and you have no problems. The problem happens is if your marble is not, or your cup is not exactly in the right place, and you want to move your marble across to the right place on the table, and then you've got some effort. And if your marble is too far away from the right spot, then you're never going to get there. A good example of this is a glider. If you let go of the controls of a glider as it is flying through the air, it will stabilize, it will settle, and it will just go at where it wants to go in a straight and steady descent. And that's great as long as that's what you want. But if you wanted to turn that glider around, it's going to take you a while. An unstable process, on the other hand, well, this is actually a neutral process, but I prefer the word unstable. It's a little bit more provocative, I guess. Here we have a marble resting on a table, there's no cup. If you make a change to that, for example, you move that marble, it will just roll. So, and it will continually rolling until it gets to the end of the table and it'll fall off. So what you do here is you have something that doesn't really resist change, it just goes with it. But if you want to control that change, you have to put in a control system. And an example of this is a jet fighter. Jet fighters are actually designed to be unstable in the air. The Eurofighter has fins on the front of the aircraft designed to make it unstable. I mean, we've been for millennia putting flights on the back of arrows when we shoot them at each other just so that they fly straight. Here with the jet, we have the flights on the front, so if the active control system wasn't working, the jet would simply fall straight out of the sky. But given that it has this control system, you can turn a jet fighter around on a dime. So if you could sort of keep that analogy in your head, this is sort of the current state being sort of stable processes, which we're all pursuing, but counterintuitively, an unstable process is where you can get better control and, in theory, a Six Sigma process. Okay, next slide, please. So I'll labor the point again a little bit longer. We have a chemical process here of compound A. We add a stoichiometric amount of compound B, and we'll get a product D out of the end of it. And that should always be great. You know, it's pretty predictable. But what happens is, and this is always the case with processes, you'll get small amounts of some variable that either you cannot measure, or you can't measure reliably. And this we call, in this example I've got is an impurity called C, and it also consumes an amount of compound B and makes another impurity. And what this leads to is inefficiencies in yield. You're making an impurity in your process. It's consuming certain amounts of compound B, and you can never get the stoichiometry right. And this sort of day-to-day variation in this variable C that you simply cannot control reflects itself in your 3 sigma distribution that you get in your process. I've chosen an organic impurity in this bit of a little bit of sort of dodgy chemistry, but it could be any variable that you simply cannot measure. In the top right-hand side, there is a chart of what happens with what we effectively call a servo control system. You're adding compound B to compound A, and it gradually reaches an endpoint as you push the material in. If you get the material the right amount of A and B together, you'll hit your target yield. If you undercharge B, you'll end up slightly low, and if you overcharge, you'll go over. But if you go over, there's no going back. You're stuck with an impurity in your process that you don't want, and you have to remove. Next slide, please. So we take that exact process and we turn it into a controllable process. In this example, I have a continuous process. So I'm feeding these reagents A and B together and making D. And what I did here in this particular example was I added a inline process analyzer that just measured what the chemistry was doing, effectively whether the right amount of product was being manufactured. So if the levels of this unknown variable C were too high, this would allow me to titrate more B into the process in order to get the exact stoichiometry that I wanted. And as a result, I'd always get the optimum production of this product, which we're calling D. Now, I hope that's simple enough to understand. But so effectively what I'm doing is, instead of doing the chemistry in one big batch, let's say, for example, in a 5,000 liter reactor, I'm doing this reaction sort of 500 mils at a time in a tiny little reactor. So if I overcharge it, then for the next 500 mils, I can adjust. And this is what we call regulatory control. So in the top right-hand side, you see a little wiggly line, and it moves around the set point that I want. That's effectively how the process operates until it finds its sweet spot, and then it settles down. And using techniques like this, we're able to achieve quite comfortably Six Sigma processes in chemistry. And we can manufacture to very tight tolerances. This allows us to operate anywhere, or rather, we can operate very close to our higher or low specification limits if we want to, without any risk of making product that's out of specification. So I hope that was all understood. All right, so my point here, I guess, is you have a process, you design it to be controllable, but in order to effect that control, you have to be able to take measurements. The little graph there says measurement predicts CQA. Interestingly here, when we made this product, rather than measuring some process intermediate, we actually predicted what our release specifications were going to be. So the release specification being the requirements on the release certificate of analysis. So we didn't actually measure in-process variables like pH or temperature or whatever it might have been. We simply predicted exactly what the certificate of analysis was going to say, and we control to that. It means that we actually know what our certificate analysis is going to say before we've even made the product. For this particular process, it's an 80-hour process, and 10 minutes into that, we know what sort of product we've made. So, all right. So, in order to get good measurements, then I'm going to change topics. Move on to the next slide, please, and talk a little bit about UV spectroscopy. Now, here's an example of a system. Imagine we have low concentrations of a monoclonal antibody in mg per mil in a mixture of DBS, which is donor bovine serum. So that's the sort of serum that you might want to grow cells in. And so we have this concoction of really concentrated concentrated protein that the cells like to live in, and very low levels of MABs that we are producing. So you can see the DBS is around about 2 mg per mil, and the MABs center point is a little under 0.2 mg per mil. So in order to solve this particular problem, we're using UV spectroscopy. We're using the whole spectrum. We're not just using a single wavelength. And I'll elaborate on that a little bit in a moment. But I wanted to show you that the calibration has a 5-point calibration, but it's shaped like a square with a center point in it. And this is effectively how you would build a 2D calibration. It requires 5 data points. If we move on to the next slide, then we take these spectra. This is a whole bunch of statistical charts for PLS. The one that's of interest is the graph at the bottom left-hand side that just shows a calibration curve. So here we are quite capable of measuring MABs in a concentrated mixture of other protein quite reliably. And it works spectacularly well, but only when your systems are very simple. One of the challenges that we have with UV, although it gives us good sensitivity, the challenge is that it doesn't give us selectivity. It's not specific enough for all the different compounds that we might want to analyze. And if you don't have a chromophore, you're sunk. So if we move on to the next slide. Here, still sticking with UV, this was to give you an example of the sorts of maths that we use and how we think about building PLS calibrations. So what we did was we were collecting protein off of a column. I hope you're all familiar with that. It's basically a large, I don't have a drawing here and I really should put one in now. You basically have a chromatographic separation occurring, and the graph on the top left shows slices of the spectrum through time, and basically the intensity changes as the protein elutes off the column. Initially on this particular system we have the protein that we want coming off, and then at the tail of the column we have protein that we don't want coming out. It's really hard to tell if the spectra are all the same or not at these different concentrations. So what we use is a technique called SNV correction, and that's on the top right-hand side. If I scale the spectra to take away any concentration information, you see they overlap all very well. And in fact, it's quite hard to see that there's any difference between them. So I then take these spectra and I apply what we call a first derivative to them, and that takes us to the bottom left. Now, what I'm showing you there is, having done all this pre-treatment, I have I've extracted differences in the UV spectra that you wouldn't have seen if you were looking at the raw spectrum. So the red lines underneath show the UV spectrum that I've treated of protein that I want, and the blue lines are the different levels of other impurities that might be present in the tail of the protein, of the chromatographic separation rather. So what this means is if I just monitor this process, I can identify when I start to get impurities coming out, and I can stop my fraction collection. The slide at the bottom left, I just wanted to zoom in and show you 280 nanometers, which is where most people work at, and it's a wavelength at which there is absolutely no selectivity between the different proteins. So if you want selectivity, then you have to use shorter wavelengths basically. So this is an example of how you can do PLS modeling on a simple system. Now I want to, if we move on to the next slide, I wanted to talk about much more complicated systems. So we wanted to design a Raman probe, which is in that picture there. You can see the Raman probe stuck into a bioreactor, and we wanted to measure lots and lots of variables in that bioreactor. Most chemically defined processes have anywhere between 30 and 60 compounds present, and we wanted to know what was going on with as many of those as we could. The sorts of variation that you'll see in a bioprocess like this are cell growth, and the different phases of the cell growth. There are changes in media composition as the cells eat the material and produce waste. There are environmental variations in terms of mixing and temperatures. pH changes occur. You have protein expression of the product getting made, which is fantastic, but that will also interfere with your signal. And then you have unwanted events, things going on that you maybe don't want to happen, but they will affect your spectra as well. So it's as well to know that those are occurring. If they occur, then you can maybe discard the batch. And of course, your equipment changes with time. People will tell you that their product is great, but swapping from one instrument to another can be problematic. If a probe breaks and you need to swap probes, they'll never be quite identical. And so these are concerns that you need to address if you're going to build a calibration for a process. Now, in a system like this, excuse me, I'll assume you all have a little bit of knowledge of cell growth and cell cultures. But as a cell is growing, it's consuming glucose and it's producing lactate as the waste product. So lactate levels go up as glucose levels go down, as cell count increases. So if you're taking a measurement, how do you know which one of those things you're measuring? Because you could probably infer how much lactate you've produced from how much glucose you've consumed. Now that's always great if your process is closed and that relationship is always true. But if you had a fed batch reactor, you might want to keep putting in new amounts of glucose periodically, and then that correlation would break down. So this we refer to as covariance. And so one of our concerns was if we were measuring an ingredient in the process, how did we know that we were measuring that ingredient specifically and not inferring it from something else? So this is so that'll go on to the next slide. But in order for this to work, some of the challenges that we're having with Raman spectroscopy are around sensitivity, selectivity, and speed. Okay, Raman is notorious for being an insensitive technique. It really, for chemical processes, people talk about having limits of about 1%, which in the biological world is ridiculously concentrated. Raman gives us selectivity, which is great, which UV doesn't have. Speed is, I guess, a relative thing. And if the process doesn't change very fast, then you can have slow measurements. But if the process is fairly dynamic, you need to be sampling your process at a rate that's faster than it is changing, or else you won't be able to tell what's going on. And then finally, we need robust systems that don't break down, or if they do break down, we're aware that it has happened. So if we move on to the next slide, please. So here we have, excuse me, I hope you can still hear me. I adjusted my headset. We use experimental design a lot of the time. So if you cast your minds back to that slide that had only 2 variables, you needed 5 points to produce that calibration. We wanted to build a system that had 11 variables in it, 9 of which we would quantify. So I've shown you a little calculation, and excuse me if it's wrong, but I seem to remember the calculation for a DOE, for a full factorial study is 2 to the n plus 1 if you have a single center point. This means that if we wanted to build a calibration with 9 variables, we would have to take 513 measurements or observations. I mean, it's a ridiculously high amount of work. So we used an alternative which is more efficient than a sort of a full DOE, and we were able to come up with a model that had only 25 variables, or 25 observations rather. I won't go into that too much today. It's the exact paper is quoted in a white paper that we did with Tornado. So if you wanted to read up on the maths of that, that's there. But the graph below shows you how we broke down the correlations between the variables. Here we have glucose and lactate, and you can tell that each of the measurements in our calibration curve is uniquely resolved from all the others, and you couldn't plot a line through there and get an R squared greater than 0. There's no covariance in our system, and you could do this for any combination of variables, and the R squared would be 0, which from our point of perspective means that there's no covariance. And if we are capable of building a calibration, we must be measuring the compounds uniquely. Okay, next slide, please. I think I probably need to chase this on. Okay, let's just whiz through just to remind you again. This was looking at acquisition. Next one, PLS, which I've talked about at length, noise filters, and process control, which I ain't going to talk about. So let's go to acquisition. On the next slide, please. This is a Tornado system that we did the study on. Most off-the-shelf Raman spectrometers, to give you some context, take 15 minutes to take a measurement. That's sufficiently sensitive. And even then, it's battling to measure anything better than glucose and lactate reliably. Here, we're using the Hyperflux Pro system. So we've got here laser intensity is almost 500 milliwatts at that source. By the time it gets out to the system, it's less than 300 milliwatts. We have an exposure time of 3 seconds. Contrast that even to a 15-minute measurement. And we're taking 15 accumulations, giving us a total acquisition time of 45 seconds. The spectra of the media are shown below. And if you eyeball them, it's hard to say that there's a lot of difference. But if you study that, you could find little nuances and differences here and there. But we rely on the maths to extract a signal from, or a measurement from that signal rather. Okay, so the next slide, please. So these are the results that we obtained for all the compounds that we were analyzing simultaneously. So I'll read through the list. There's glucose, lactate, glutamine, glutamate, which are present normally at fairly high levels in a bioreactor. Then we studied some essential amino acids that are present at much lower levels: histidine, leucine, arginine, and phenylalanine. They have different degrees of challenge. Phenylalanine being really easy to analyze by Raman. It's a strong Raman scatterer. Arginine being a terrible Raman scatterer. And then finally we analyzed ammonia, which will be present as an ammonium salt in the mixture with cells. So you can see from these charts that we were able to build some pretty good calibrations. Now, we've not been able to replicate these results on any other Raman spectrometers. It's my own personal view that this instrument is giving us between 10 and 20 times more sensitivity than the other equipment that we evaluated. So things like glucose and lactate we can measure spectacularly well. Phenylalanine I talked about, ammonia we can measure. The one that we really struggle to measure is arginine. And I believe that that's probably reflects something more complicated going on with arginine rather than a weakness in the Raman scatter. I think there's some sort of concentration dependency that I think the spectrum changes. Because to my mind, when I look at that curve, there's almost like some sort of residual error that's shaped like a signal curve. But I don't know, I speculate and I raise it because the subject is of interest to me. We haven't got to the bottom of why that occurs or why arginine is uniquely difficult to quantify. But we have a calibration that would satisfy our requirements at least. So I'm going to move on now and change gear yet again and talk a little bit about noise and normality. So this is one of the challenges that we have is if when people look at the error in our prediction models, they say, oh, that's not precise enough. But you can address precision and accuracy errors through signal smoothing. So here I have a graph which I've created some synthetic data. The gray line is just the signal, it's just a Gaussian noise, and you can smooth that using either a mean, which is which we refer to as the most simple linear filter, and a median, which is referred to technically as a non-linear filter. Now, if your system is not changing, median and mean filters have pretty much the same effect. You simply reduce the noise in your system and you get a better average of what's going on. Things get interesting though if a process change occurs. So here we have, if you look at the gray line, we had a sudden step change in our process, and then the process continues at a new set point. The average system, although it starts to change or starts to respond to that change more quickly, reaches the endpoint a lot more slowly than a nonlinear filter. The nonlinear filter doesn't react at all initially, and then suddenly when it decides the process has changed, makes a step change to the new set of conditions and proceeds. So overall, using nonlinear filters to denoise our signals generally works much better than your standard averaging that everyone that I deal with tends to just gravitate to immediately. The next example is gross error, which is the final phase of this chart. I added a data point that was clearly not part of the other data set. It's a gross error. It's enormously different. And if you put that, if that was to happen with your spectrometer in a manufacturing process, that value would get stuck within the mean signal for a while afterwards. So if you have a look at the blue line, you're stuck with an offset for a little while until you moved a sufficient distance from the gross error, and then you're back at the set point. The median, on the other hand, it does not even see the gross error, it just ignores it entirely. So there's a whole field of science dedicated to nonlinear filters, the median being the very simplest one, and you can make it as complicated as you can, for Freudian, as complicated as you want. I can show you where we've used some more complicated filters in the next slide, please. Right, so here we have a Raman spectrometer. This was not a tornado, this is one of our earlier experiments where we're trying to measure glucose and lactate in a bioreactor. If you look at the red graphs on the left-hand side, the measurements are incredibly noisy. So you can see there's a lot of random error, but there's also a lot of gross error where you can see spikes influencing the data. So what we did here was we used nonlinear filters to clean up the signal, and you can see then on the right-hand side, the clean signal follows the reference values much more closely. And so we take a system that's barely capable of measuring the thing that we're interested in and extract from that noisy signal a fairly reasonable approximation of the truth. So not all the problems have to be solved with the spectrometer. You can solve these downstream with the PLS or with noise filters afterwards. So finally then, I have one more slide, and I'm sorry I have overrun a little bit. I will just move on to the last slide, please, and talk a little bit about industrial installations. It's all very well to build these calibrations and have them all working, but the problem is that once you've built something and stuck it in a production plant, if you're reliant on it, you have to make it work all the time. And that is not so easy. There are three things to think about if you're putting a Raman spectrometer into a production plant. The first is sampling error. What this means statistically is that my sample is not representative of my process. What I'm looking at is not the truth of what's going on in my process. I have faulty information, and so I'm reacting to the wrong things. And the reasons this happen is our sample size is too small or irrelevant. Our sampling point is irrelevant if it's not representative of the whole, or our probe is fouled and it's just measuring something else entirely. Equipment differences are a challenge, and we try to build these into our calibrations as much as we can, using multiple spectrometers, multiple fibers, and multiple probes, so that if you need to switch equipment, you can do this without getting too much bias or any other errors. Finally, if we're putting a spectrometer into a production plant, we generally perform a risk assessment called an FMEA, which is a failure modes and effects analysis. So we think about how this equipment will break down once it's in a production plant, how likely that is to happen, and then what would happen if the equipment were to stop working. What would be the consequences for the batch? How would you even know that your equipment had broken down? How soon, before you reacted to it? And then finally, once you knew that something had happened, what would you do about it? And I find that a lot of folks don't give enough thought to that up front, because those are the questions that you really need to address, and that is what the target looks like when you start out in the first place. So knowing where you're going to end up at the end of all of this development cycle will keep you steered in the right direction. So at the end of all that waffle, next slide please. I am done.
All right.
Thank you for listening.
Thank you very much, Dylan, for your excellent presentation. We now have the pleasure of addressing any live questions. As I mentioned before, please feel free to use the chat box located within the menu, and I will read the questions as they come in. So if you have any questions, now is your time. All right, well, I guess that was a fantastic presentation, and there are no questions. If there are questions after the event, then you can contact Dylan Jones. His contact is on the screen. I would now like to thank everyone for taking the time out of their busy schedules and being with us today. We hope you found this webinar very informative. On behalf of Tornado Spectral Systems, I'd like to once again thank everyone for attending. For a more detailed list of events, you can visit our website at tornado-spectral.com and visit the news and events section. We'll be hosting more webinars in the future, and keep an eye out for our events and the trade shows that we'll be attending as well. Thank you, everyone, and I wish you a great rest of the day.